The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, my name is Shuha Soila and I'm the Director of Operations at Hosokawa Micron Powder Systems. We at Hosokawa Micron Powder Systems welcome you and thank you for attending our next in the series of educational webinars entitled Benefits of Finer Trona Particles Sizes in Flue Gas Desulfurization. Let me point out, if you have a question during this presentation, you may submit your questions online at any time. Please refer to the Q&A pane on the right of your screen. At the conclusion of the webinar, we will try to accommodate all the questions during our question and answer forum. Hosokawa Micron Powder Systems is a division of Hosokawa Micron Group with headquarters in Osaka, Japan. We are a global leader in powder processing equipment with over 1,500 employees worldwide, production facilities in 5 countries, and 12 research facilities and state-of-the-art test centers. Hosokawa Micron Powder Systems, founded in 1923 under the name of Pulverizing Machinery, is responsible for the North American market. We, from Summit, New Jersey office, provide full sales, engineering, manufacturing, and aftermarket services for the chemical, mineral, food, and pharmaceutical industries. We are the proud inventors of the micropulverizer hammer and screen mill, as well as the most versatile air classifying mill, the ACM. Our brand names include Micro, Alpine, Reconauta, Majak, Micron, Stott, and Vital Air. At this point, I would like to turn the presentation over to Mr. Bill Brown, who is the Division Manager for the Chemicals Minerals Group. Bill, who has been with Hosokawa for the last 18 years, has earned his Master's in Business from University of Richmond and his Bachelor's in Engineering from Rutgers University. Bill's primary fields of expertise is toner, Trona, and carbon black, yet he has been involved in development of multitude of specialty processing chemicals and minerals industries. With that, I would like to turn the presentation over to Bill.
Thank you, Suha. Let me begin by outlining the topics that will be covered in this presentation. As a focus of this webinar is related to the effects of size reduction of the sorbent reagent for dry sorbent injection, I will begin by highlighting the advantages of dry sorbent injection. Next, a comparison of 2 types of sorbents, Trona and sodium bicarbonate. The effects of sorbent particle size on sulfur dioxide reduction. Optimum milling technology for particle size reduction. General size, production, and performance data, followed by a summary and question and answer forum. Fossil fuels such as coal and oil contain significant amounts of sulfur. When burned, over 95% of the sulfur is more or less converted to sulfur dioxide. Typical applications include utility and industrial boilers, in addition to other types of combustion units such as municipal and medical waste incinerators, cement and lime kilns, metal smelters, petroleum refineries, and glass furnaces. Flue gas desulfurization is an absorption and reaction process using alkaline reagent to produce a solid compound. A technology for removing sulfur dioxide from exhaust flue gases. As you know, sulfur dioxide is a harmful pollutant responsible for acid rain formation. Flue gas desulfurization technology has been around for approximately 100 years, but over the past couple of decades, U.S. federal and state regulatory agencies have been tightening emission standards. Additional regulations are imminent. We expect to be subject to even further reduction in sulfur dioxide emissions in the upcoming years. At the present time, of the flue gas desulfurization systems in the U.S., approximately 85% of them are wet scrubbing systems. Approximately 10 to 12% are semi-dry or spray-dry systems. And finally, 3 to 5% are dry systems. Typically, the highest sulfur dioxide removal efficiencies can be achieved using wet scrubbing with removal rates greater than 90%. A dry sorbent injection system, or DSI, is a dry system. It's a process in which a sorbent is pneumatically injected into the furnace or downstream ducting. The dry waste product is removed using particulate control, such as an electrostatic precipitator or baghouse. So that raises the question, why dry sorbent injection? Well, first, the capital cost of wet scrubbers and semi-dry systems are much higher, as well as perhaps the operating costs. In addition, these types of systems, being wet scrubbers and semi-dry systems, take up much more space. Traditionally, dry sorbent injection systems can achieve removal efficiency as high as about 80%. However, for quite a number of more recent smaller industrial applications, we can expect removal efficiencies of greater than 90%. And also, with further adjustments to the process, higher removal efficiencies can be achieved with even less reagent. With respect to dry sorbent injection systems, there are two primary sorbents utilized, and they include sodium sesquicarbonate, or Trona, as well as sodium bicarbonate. Trona is a mineral. It's a mine material. It's a natural form of sodium sesquicarbonate, and it's with the primary location being formation in Green River, Wyoming. However, there is another location in the United States. Sodium bicarbonate, on the other hand, is a chemical compound or a salt, primarily manufactured using the Solvay process. This salt is obtained from a reaction of calcium carbonate, sodium chloride, ammonia, and carbon dioxide in water. There are several notable differences between these materials. For one, sodium bicarbonate, simply put, it's more effective in sulfur dioxide emissions than Trona is. Hence, less sodium bicarbonate could be required for an equivalent removal. However, sodium bicarbonate is much more expensive in the United States. For Trona, as I mentioned in the previous slide, this is a naturally occurring mineral with a vast formation, obviously, in the United States. So there is by far an abundant supply here in the States. However, for plants outside the United States, logistical costs may prohibit its use, despite the fact that Trona is approximately half the cost of sodium bicarbonate for a wide range of sizes. The effectiveness of sulfur dioxide reduction is based on the following factors. Please note these factors are not ranked from highest to lowest contribution. 1. Sorbent injection rate. Sorbent resonance time in flue gas stream. Sorbent penetration and mixing with flue gas. Particulate control device, such as a baghouse or electrostatic precipitator. Flue gas temperature. And finally, the primary focus of this webinar, sorbent particle size. Please refer to the graph, which shows the correlation or effect sorbent particle size has on sulfur dioxide removal efficiency. This graph is based on data compiled from a multitude of lab tests, in addition to real-life actual results or feedback from our customers utilizing air classifying milling technology. On the x-axis is particle size, referred to the term D90, which is the size expressed in microns at which 90% of the particles are finer than. On the y-axis is sulfur dioxide removal efficiency. As you can see from the data here, as the particle size distribution is finer, you see here from 100, for example, down to 20 microns, the sulfur dioxide removal efficiency increases. Traditionally, power plants have utilized coarser grades of sorbent, perhaps in the D90 range of between 75 and 100 microns. For these applications, removal efficiency is low as compared to other types of flue gas desulfurization systems. However, when injecting finer sorbents, let's say in the range of 20 to 30 microns with respect to the D90, removal efficiencies approach alternate technology results. This graph here shows a particle size distribution for Trona produced by an air classifying mill. Particle size here was measured using a laser diffraction device or analyzer, the method of which is utilizes laser light scattering and produces a probability density function as shown here. This actually represents perhaps near the finest particle size condition achieved on an air classifier mill for this particular application. As you can see, This application required an end product with a median size, or D50, of approximately 5.2 microns, as shown here, with a D90, or nominal top size, of approximately 10.6 microns. Please note, this is a typical curve or profile generated by an air classifying mill. Note the very steep coarse tail here. This is a feature of the air classifying mill. By utilizing an internal dynamic classifier to control particle size, particle top size that is, a narrow particle size distribution can be achieved. The next graph shows the effect of particle size on energy requirement. In other words, the relationship between particle size, in this case, instead of D90, I have here plotted D50 or median size, versus the capacity of an air classifying mill or a typical air classifying mill. For this plot, we have selected a pilot size air classifying mill employing a 15 horsepower main grinding motor. This graph more or less shows the full workable range of an air classifying mill, down to approximately a median size of around 5 microns and upwards to a median size of, let's say, 30 to 35 micron range. For dry sorbent injection applications utilizing an air classifying mill, most common particle size ranges are in the 10 to 20 micron D50 or median size range. However, in recent years, there has been an increase in demand for even finer grades of sorbents, from a D50, let's say, of around 5 microns to perhaps 8, 9, 10 microns in range. In the case of the particle size distribution outlined in the previous slide, with the median of 5.2 microns, you can see here that utilizing a 15 horsepower mill, we can achieve on average of about 100 to 120 pounds per hour. However, if trying to achieve a 15 micron D50, and looking at the plot here, the output increases substantially, from 100-ish pounds per hour and upwards of 750 pounds per hour. The energy requirement can also be expressed differently, perhaps in terms of output of product per unit of grinding energy input. Energy input is electrical energy required for grinding, in terms of perhaps horsepower or kilowatts, let's say. Output can be expressed in terms of pounds per hour, kg per hour, tons per hour. And in producing a 5.2 micron material, for example, approximately 7 pounds per horsepower hour is required. However, in the case of that 15 micron median size range, the per unit rate or specific energy is up to 50 pounds per horsepower hour. So again, there's a substantial improvement in milling, or let's just say it's less energy intensive to produce a 15 micron material versus a 5 micron material. So as you can see here, the particle size of the end product does have a significant effect on capacity. This table here is more or less a quick reference chart to determine air classifier mill size for a particular capacity requirement for two common sorbent particle sizes. What I've shown here are two different D90s, a D90 of 20 microns and also a D90 of 30 microns. The column on the left shows common production size air classifying mills from 30 horsepower and upwards of 350 horsepower. The rates shown on this table are nominal rates for Trona and are expressed in pounds per hour. Again, on this chart here as well, you can see the effect of particle size on mill size for a given capacity requirement. A 20 micron median sized sorbent requires almost double the energy than a standard 30 micron product. While a finer sorbent particle size increases sulfur dioxide removal efficiency, it is done so at a cost. You'll need less 20 micron product than 30 micron product perhaps to remove X percent of sulfur dioxide. However, the energy requirement is higher to do so. So there does exist a trade-off between particle size, the amount of material required, hence material costs, and operating costs. Pictured here are two common air classifier mills. The image here on the left is a 300 horsepower mill with an independently driven classifier wheel. The classifier wheel for this particular mill is of size 50 horsepower. Nominal rates are approximately 5,000 and upwards of 20,000 pounds per hour, depending upon the particle size requirement of the sorbent. This particular mill, dimensionally, is approximately 4 meters by 1.5 meters by about 3.5 meters tall and weighs in excess of 8,000 kilograms. Nominal airflow range for this size mill is about 15,000 standard cubic feet per minute, or in other words, about 25,000 cubic meters per hour. The image on the right shows a 75 horsepower air classifying mill. This particular mill has a classifier wheel that is driven on the same shaft as the rotor. This size mill can achieve rates in the range of about 400 pounds per hour and upwards of 3,000 pounds per hour, again depending upon the particle size requirement of the sorbent. This particular mill dimensionally is about 2 meters by 1 meter footprint, and it's approximately 1.8 meters tall and weighs in excess of 2,000 kilograms. The nominal flow rate for this particular mill is about 3,000 standard cubic feet per minute, or almost 5,000 cubic meters per hour. Facts and features of a typical air classifying mill. They include the following. High tip speeds in the range of approximately 115 meters per second, or about 23,000 feet per minute. 115 meters per second, or 23,000 feet per minute. The mills are equipped with an internal dynamic classifier wheel, shown here. This particular classifier wheel, or the classifier wheel for the air classifying mill, does control the top particle size. There are two designs of an air classifying mill, one including an independently driven classifier wheel, as in the previous slide would be the image on the left, using a separate separator or classifier motor, and one with the classifier wheel driven on one common shaft with a grinding rotor, in which case in the previous slide it was the smaller mill on the right side. This design can be determined based on testing or based on customer requirements. One other important feature to note is that, as the name suggests, this is an air-swept mill. Airflow is an extremely important parameter which affects size reduction and classification efficiency. It not only affects size and efficiency, but also serves to cool the material being processed. The amount of airflow per given grinding rotor size, as compared to, let's say, a pin mill, for example, is higher. And so, there is a natural cooling effect that does take place, and hence a lower product outlet temperature could be achieved with this type of mill. What we're showing here in this next slide is a flow pattern in a typical air classifying mill. The main principle of this mill type is to air convey the material to the mill, classify the product into a fine and coarse set of fractions, convey the fines out of the mill, and then return the coarse fraction to the grinding zone for further size reduction. This process is repeated on a continuous basis, and this unique feature of this type of mill is that the classification step takes place inside the mill and is not a separate or external operation, perhaps like a pin mill, for example. This design also allows these mills to be relatively compact and small in size. Now what we have here is the main airflow is introduced underneath this rotor disc. So the air is coming in here below the rotor disc. What we're showing here is the rotor disc, and in this case bar-type hammers or beaters. Material is being introduced into the grinding zone right here at this point, right at the path of the hammers. The particles are impacted by these rotating hammers. Processed material is then carried by the airstream to the classification zone, which is located right here. Correctly sized material, or material fine enough, passes through the classifier wheel, and it exits and then gets conveyed to the material handling fan. Oversized material is rejected. It drops down in the center of the mill and is then forced out due to the centrifugal force and is redirected to the grinding zone for recycle of grinding. The grinding and classification zones are normally separated by a shroud and baffle assembly shown here. Next, we have a schematic of a typical air classifying milling system used in dry sorbent injection systems. Here I've highlighted the air classifying mill in this process. Feed material is transported via rail car or perhaps by truck to one or a series of feed silos. The feedstock is then metered into the mill, shown here. The ground sorbent, which is done in the air classifying mill, is then, the fine particles are conveyed through a material handling fan, shown here. The ground sorbent is conveyed by a material handling fan, like I just mentioned, into this duct here between the combustion chamber and the bag filter. The solids are then removed at the discharge of the bag filter, while the clean gas is emitted through the stack. What I have here is another flow diagram. The feed silo holds a campaign of feed material. The feed system typically consists of a screw conveyor or screw feeder, which meters the material into the air classifying mill, in addition to a rotary airlock, which serves as a suction pressure isolator. Oftentimes, air filters are utilized to keep out contaminants. Next, we have the air classifying mill, which is the size reduction device for the dry sorbent. As I mentioned in the previous slide, the material, or the ground product from the air classifying mill, is pneumatically conveyed to the material handling fan. And from that point on, it is conveyed via positive pressure to the bag filter and ultimately to the stack. That is, the clean gas is emitted through the exhaust stack. And there is, of course, a control system to ensure proper operation, sequencing, and alarm management. Pictured here is a plant utilizing a common size air classifying mill for this particular application. The feed silo and screw feeder are mounted above the mill. You can't quite see it in this diagram or this image here. However, the air classifying mill is shown in this photo right here. This particular mill is a 75 horsepower mill. From this point on, the product is discharged through this convey pipe to the material handling fan shown here to the right, on the right of the image. And at the discharge of the material handling fan, it is then conveyed via positive pressure to the next step, typically the bag filter. Also, what I have shown here is a sketch of the system, of this particular system. So again, noting here, what we're showing here is the rotary airlock, which is your pressure or suction isolator, your feed pipe to the air classifying mill, the discharge pipe to the material handling fan, and then ultimately out to the bag filter, followed by the exhaust stack. Again, this is a common system, a common size reduction system for processing of sodium bicarbonate or Trona. In summary, government regulations are forcing lower and lower emission standards. Dry sorbent injection may be a lower capital cost alternative for sulfur dioxide reduction. The reagent particle size greatly affects sulfur dioxide removal efficiency. Utilizing finer size sorbents may drive capital as well as material costs even lower, provided less quantities of sorbent would be required to meet removal efficiency. An air classifying mill is by far an excellent choice for continuous, energy-efficient production to very fine particle sizes, and hence higher removal efficiencies. Higher sulfur dioxide removal efficiencies go hand in hand with further tightening of emission standards. And finally, cleaner emissions obviously protect our environment. Thank you very much for your time and attention.
I'd like to thank Bill now for this very informative presentation, and now we can begin our question and answer forum. As we are limited on time, we will try to accommodate all the questions, but apologize in advance if we are not able to answer all of them. If we're not able to address your questions at this time, Someone from Hosokawa will respond to you offline at a later date. First question, Bill. My company has been using pin mills for the past 10 years to mill Trona. Can you comment on how pin mills compare to an air classifying mill?
Sure. Well, first of all, when comparing a pin mill to an air classifying mill, there are some notable differences. Again, first of all, a pin mill typically does not reduce the particle size as fine as it does with an air classifying mill. Typical applications or particle size ranges for a pin mill could be, let's say, a D90 of maybe 75 microns and higher, notably 75 to 125 micron top sizes. In addition, a notable, let's say, factor or feature with a pin mill could be that it does tend to make a wider particle size distribution than an air classifying mill. As you mentioned in one of the previous slides, the air classifying mill, since it does utilize an internal dynamic classifier, which controls top size, it then hence does make a narrower particle size distribution. And perhaps the most important feature with respect to particle size distribution is with a pin mill, the feed rate does have a very direct influence on the particle size of the end product. If you tend to push the feed rate to a pin mill, you may find the particle size may tend to get coarser, whereas typically with an air classifying mill that doesn't happen.
Another question. We have been exploring the possibility of purchasing the raw material already to the finer particle size. What is the difference between purchasing the fine feedstock versus milling the feedstock on site?
Let's see. Well, based on feedback from our customers, what we've been hearing over the past, let's say, 6 months to a year or so, is that those companies that either have explored purchasing finer feedstock or they have been doing it for a period of time, they had mentioned that there perhaps are some difficulties in handling the finer feed material. For example, if the material is coming in to the plant via rail car or truck, for a given amount of massive material, it does tend to take up more volume. So you'll ultimately need more rail cars and more truckloads of material, volume-wise, for the same weight. There also have been some problems or adverse conditions in handling the finer feedstock on site. There tends to be, on occasion, some poor flow problems or poor flow properties with the finer feedstock in feed silos. Material is having difficulty coming out of the feed silos. So those are perhaps two of the biggest, let's say, maybe issues or concerns using the finer feedstock. Now, in considering the coarser grade feedstock, my assumption is, number one, it would be cheaper, less expensive to purchase the coarser feedstock from the raw material supplier, since the raw material supplier doesn't have to process it on site. So my assumption is the cost per ton would be less. Secondly, I'm assuming the logistical costs will be lower, since for, say, a ton of material, instead of one rail car, you need a half a rail car. In addition to that, once that's pumped into or conveyed into your feed silos, my assumption is that you'll have less problems in handling those feed materials.
As a follow-up to this question, Bill, I just want to continue with a question on the feed again. Can you please comment on typical or acceptable feed size that can be handled?
Well, the air classifying mill is used for many more applications than this particular application. But generally speaking, an air classifying mill, we could accept, this type of mill can accept feed sizes as fine as 60 or 70 microns, most commonly in the range of 100 to 200 microns, but as coarse as fractions of an inch in particle size. There would be a slight impact on capacity for a given end product particle size distribution. In other words, saying that the particle size of the feed will have a slight impact on the capacity. But generally speaking, this type of mill can handle a wide range of feed sizes. And for this particular application, what we've seen is the feed stock is normally in a range of 100 to 200 microns in particle size.
In And again, just a little further follow-up on it is, can we, I guess, realistically say that as the mill size gets bigger, the capability of the mill handling larger particle size is going to grow? Is that correct?
Well, yes. If we're comparing a lab-size mill to let's say a 350 horsepower mill, obviously a lab-size mill, the volume of the grinding chamber may only be a half a liter in size. So the feed opening may only be a quarter of an inch in diameter. In comparison to a 350 horsepower mill, where the inlet throat size may be 8 inches by 15 inches. So yes, a larger mill can handle a larger feedstock size.
What is the type of wear protection options available, and is there a difference in terms of a pin mill versus an ACM?
Let me address the pin mill versus the ACM. Working for a powder processing equipment supplier, we find that pin mills are limited as far as wear protection goes. There are ways to wear protect a pin rotor. However, there are many more options and many more variations for wear protecting an air classifying mill, due to the fact that you're talking about utilizing a bar or plate type hammer, which has a lot more surface area. With regard to the different ways to wear protect an air classifying mill, some of the most common ways are using tungsten carbide tipped hammers. That would be tungsten carbide tipping on the leading surfaces of the hammers. Perhaps a hardened wear plate on the top of the rotor disc. Hardened steel liners, perhaps ceramic liners even. Some other options we could even, for very, very abrasive materials, spray coating the vanes of the classifier wheel. So there are a multitude of ways to wear protect an air classifying mill for even extremely abrasive materials.
What is the typical temperature rise during milling? And, you know, I guess as the particle size gets finer, does the temperature go up with it?
I'm going to answer the second part first. As you're milling it finer, typically, there is a higher temperature rise. In the case, for example, that I showed in producing or manufacturing that 5.2 micron D50 material, as I recall, the outlet temperature in that particular case was around 140, 145 degrees Fahrenheit. Most notably, for an average particle size range, sorbent size range of let's say 20 to 30 micron range, I believe the temperature is most likely, this is off the top of my head, maybe 125 to 130 degrees Fahrenheit. So in saying that, I like to say that the average or nominal temperature rise for this application is in the range of 30 to 50 degrees, depending upon the degree of fineness.
What is involved with respect to cleaning and maintenance for an air classifying mill?
Well, as I showed in the images of the two size mills, the 350 horsepower as well as a 75 horsepower mill, even a 350 horsepower mill is not very large. It's as I mentioned, it's about 9 or 10 feet tall. We have on the air classifier mill a series of access doors, no matter what the size is. So with regard to cleaning, it's quite easy. With the access doors, a majority of the internal parts can be accessed without having to completely disassemble the mill. So for applications where perhaps there's some scaling or cleaning required every 3 to 4 weeks, that cleaning could be done with an access door, or for some of the smaller to mid-range production size units, having the top section on hinges. So with respect to maintenance, let's say, aside from checking for buildup or whatnot every, say, 3 to 4 weeks, in certain applications we've seen, the normal PM schedule or preventative maintenance schedule with respect to checking conditions of parts for wear or for lubrication, checking every, let's say, perhaps 2 to 3 times per year. Now, for most production ACMs, we recommend replacing bearings roughly every once per year or once every 18 months.
What new trends have you seen in the FTD industry with regards to milling requirements?
Well, what we've seen, what our group has seen here, and in talking with others in the industry, other players in the industry, is that it's new. This is still new to everybody. As far as what we're seeing is the trend to go finer and finer with respect to particle size. There's a growing concern that due to upcoming regulations here in the U.S. at least, or let's just say not knowing the details of these upcoming regulations, how much cleaner these emissions have to be and how much more there has to be in a reduction of the sulfur dioxide. So in saying that, there has been more and more request and demand for reducing the particle size even finer. So let's say 5-10 years ago, we're providing air classifying milling systems to handle particle sizes in the D50 range, let's say 30 microns, or in this case a D90 range of maybe 60 or 75 microns. A majority of our applications these days are D90 or top size is anywhere from 10-12 microns and upwards of 20 microns. So what we're seeing is a shift, going finer and finer in particle size of the sorbent.
Last question. Can the air classifying mill be switched from sodium bicarbonate to Trona or vice versa?
Well, sure it can. Based on testing, we do find a slight degree in the difference in the way they process, meaning for a given particle size requirement, there may be some differences in process conditions. Rotor speed, for example, or maybe airflow would have to be modified slightly. To answer that question, if a plant has a particular mill installed and they're making a change, let's say for example from sodium bicarbonate to Trona, the answer is yes, that same mill as it's constructed can also mill this other material. However, there may have to be a slight change in one of the parameters, being a speed, a rotor speed or airflow, for example, but one mill can do both. Those conditions or those operating parameters can also be determined from testing on a pilot-sized mill if need be.
We at Hosokawa Micron Powder Systems sincerely thank you for your time and attention today. If you have any further questions or requests, you may contact Bill Brown directly from the number shown on your screen. One other note, this presentation will be posted on our website, so if you know of any colleagues who may be interested in viewing this or any of our prior webinars, they may do so by accessing our website in the educational tab there. Again, we thank you and have a nice day.